directed acyclic graph. Direct, directed means there is a direction, and then acyclic means there is no cycle. There's no cycle. There's no roof, and the graph. So this one is reference is the book. It's a causal inference in the statistics of Premier. And also I refer to some YouTube video, which is the like online workshop, and I refer the slide and contents from that YouTube video. Structural causal model, so SCM. That's a structural causal model. So definition of causation is that when variable x is directly cause of the variable y, if x appears in the function that assign y's value, and we call x is cause, if this is a direct cause of y or any cause of y. So example is that this is the structural causal model. So u and v, this is the one is here the endogenous variable. Endogenous variable means it's inside, right? Exogenous variable. So exogenous is from outside. So exogenous variable cannot be a descendant or of any other variable. So exogenous variable should be by itself. It's not caused by any other variable we are considering. But endogenous variable will be affected by the some variable. Okay. So that's the example. So U is the exogenous, which means x and y is the variable that is just variable. It's not caused by any variable we are considering. Okay, so it may be caused by something, but we are not considering the other thing. X and y is just from outside, but z is the variable which that affected by the f. So if you draw the chart, x will affect the z, and y also affects z. So x and y is not a descendant of any other variable, but z is a descendant of x and y together. So if you have this kind of formula, so z, this is function z equals 2x plus 3y. Actually, it's the same as this one. X and y are cause of z, right? And this is what we call the structural causal model, SCM. Every SCM is associated with a graphical causal model. Graphical causal model is this one, and as you can see, there is a direction. There is always has an arrow. So diagram has a direction, right? This is not going backward. Okay, this is has a direction. That's why it's directed. And acyclic means it's not having any roof. If this one goes here, then you can have a roof here, right? Or if you have like 4 of them, if this one goes this one, this goes this, and this goes this, and this goes this, this has a roof. We should not have this kind of roof. So acyclic means there is no cycle, which means no roof. Oh, there is no circular path, acyclic. So causation is the changing x will change the probability of y in the stochastic world, or if we change x and y will change, or in some case we call y listen to x. And then we draw a diagram. I should have a large head of the arrow. And we draw the direction, so x cause y. This is causation. This is a causal DAGs. So it can be like a really complicated. So B codes C and B codes F, A codes C and A codes F, or C codes D and F, and then D codes F, and then E codes F also. So how can we find out the DAG? So there's no analytical way to find the correct causal DAG. So what it means is that once you find out the DAG, you don't know that is correct one, and there's no way to find the correct one. Actually, you will never know what is the correct causal DAG. But we're trying to make it correct as much as possible, but you will never know it's actually correct or not. But it can help to build the causal model and help us to choose appropriate estimator and helping a lot. So this is quite useful tool, but this cannot resolve any analytical answer. So this is easy to identify and easy, the helping avoiding some errors, but we cannot know the real data generating model, which is the which cause what and which cause what. Even though I draw the my guessing DAG, but you will never know this is correct or not. So what we are trying to do is to choose the best possible estimate. So path is the connection by one or two arcs. So actually, the simply one connect, this is the what we call path. Or if you move here to here to here, this is also path. And this one, even though the arrow is coming here and here, this we also call the path. So this is a regardless of the arrow direction. If it's connected, and we call this is the path. Now compounding path. What is a compounding path? We already know if there is a common cause. Right? So A cause C and A cause F, then really C cause F or not, actually we don't know, but because of A has some kind of effect, right? So if you really want to know the C, how C affected F, then you have to cut off this effect, compounding effect. But first you have to find out what is a compounding. So this is sometimes we call this a backdoor path. Actually, it's going back door, and then you can go to the front door, but this is a back door. So it's a compounding path, and this is open. So I will talk about what is open and closed. Open without conditioning. Without conditioning is you just restrict something. So you don't restrict anything here. ACF, relationship of ACF. What you are expecting? Since A has a common cause, C and F will have some correlation. There will be a correlation. So C and F will have a correlation. That's what I mean is open. I'm not saying the C cause F. We don't know yet, but we can tell there is a correlation. So C and F is connected. It's open. However, if we restrict the A, right, then we can cut off. Then C and F may or may not have the correlation. So I will show you the example in the very simple one. This is when we conditioning on the A, we condition on the A, then the path is closed. When we close this path, conditioning A, if after that still C and F has a correlation, then we might say C cause F. Actually, there is another compounding path, so you have to cut off this one also, cut off this one also. Now, if you just take a look at the relationship between the C and F, then you can tell, oh, even without the cutting off all the compounding effect, still C has a correlation with the F, then we can say C cause F. So let's look at the example here. The conditioning means is estimating the statistics at fixed level. So this fixed is an important word here. So the conditioning, sometimes conditioning means a restriction. I'm only looking at the non-smoker only, or the stratification is you just creating the class, or you can using the covariate adjustment. But you can right now you can just think this is just simply restriction. You know the ice cream hazard problem. This is when you ice cream consumption has associated with a high incidence of the shark attack. So if you eat more ice cream, there is a high probability you can attack by shark. So don't eat any ice cream. Yeah, of course this is not true. Why these things happen? Here associated, which means there has a correlated. Right? High ice cream consumption has a correlation with a high incidence of the shark attack. So you should not eat the ice cream to avoid a shark attack. That's not true. But actually what happened is when the weather is like a hot day, people eat a lot of ice cream, and also they go to a lot of people go to the ocean. That's why we have a high incidence of the shark attack. So high temperature, hot weather cause both of them. So in that case, this is a confounder. If we condition on the weather, how can I conditioning on weather? If we consider only the hot day, really hot day, not the cold day, hot day, I'm only looking at the hot day. So it's like a temperature is higher than 35 Celsius. I'm only collecting the data, really hot day only, Is it still has a correlation between the ice cream consumption and shark attack? Maybe not, right? So if both of them will have a really high consumption and high shark attack. However, if we collected only hot day data set, still ice cream consumption will have a correlation with a shark attack. Probably not. But if we can see, if I condition on the only hot day, still ice cream consumption has a correlation with the shark attack, then we might believe the ice cream consumption has some cause effect on the shark attack. So that's what I mean is a conditioning. If we only take a look at only the cold day, only, it's like temperature is between 5 Celsius 5, between 5 and 0. We collect only that data. Still, ice cream consumption and the shark attack will have a correlation? Probably not. So that's what it means. It's with the conditioning, this is closed, right? This effect, compounding effect, is closed. So this is kind of conditioning. So it will be, this path will be closed with the conditioning. It's open. Without conditioning. because still we should be able to see the correlation between these two numbers if we don't condition on the weather, which means I open the door, back door, I open the back door. Even though ice cream is not cause the shark attack, still using the back door we can see the correlation. That's what I mean is open. Close the path means you cannot, without the real cause, you cannot take another path. Ice cream can has a relationship with a shark attack without the direct cause. So we can take it out to the compounding effect. So okay, so this is open unconditional dependency and close with the conditioning. So unconditional case, this is open, and under the condition, this is closed.